Welcome back to the Lead channel. On another episode looking at dynamics and forces. Today we're going to look at inclines. I'm going to try to break this session into 3 independent videos and to try my best to keep them short. Before you watch this video, you really want to make sure that you've watched 3.06 IB material on equilibrium and looking at how to resolve components of forces before tackling this one, because we're going to look at what happens if an object moves, looking at how the forces play there. Specifically, we're going to look at inclines. What happens to an object if we put it on an incline? Before we even deal with that kind of situation, we're going to work our way up there. Let's start with an example. Let's say we have an object, and let's say this object is lying on a flat surface. So drawing a free body diagram, we know that there's force due to gravity acting on this object. Also, the normal force, which is a reaction force coming from the ground that is equal and opposite to the direction of gravity so that the object doesn't move. Now, what if I told you that this object is sitting on a plank, a wooden plank, and let's say that I am able to take this wooden plank and start to move it upwards, okay? So if I tilt this wooden plank upwards, what I'm going to get is I'm going to get a plank that is sitting on an angle, and I have an object now probably not going to be able to stay still. Will roll down the incline. So looking at this thing, let's draw the free body diagram here. Now, one might be very tempted to draw the gravity sideways. But does gravity work sideways? No, it doesn't. Gravity doesn't pull you sideways. Otherwise, you'd probably be on the corner of the ground or something. Gravity acts always towards the center of the earth. So in this case, even though you're on an incline, gravity is still pointing down. However, there's an interesting thing now, because notice that your surface is no longer vertical, no longer horizontal, but it is on an angle. If you have a surface that's on an angle, 90 degrees or perpendicular to that is no longer going to be just your regular old vertical or horizontal normal force, but your normal force will have to be 90 degrees to that surface and on and diagonal. So this is something interesting that you've never seen before, is your normal force pointing at an angle, but that's just because you have an angled surface. Now let's keep moving this plank upwards. Let's say you keep moving this wooden plank upwards to the point where it's completely vertical, okay? If you think about this plank completely vertical, is the plank going to be exerting any force on the ball in a sideways direction? Well, I mean, if you're completely vertical, and let's say the ball is able just to drop, it's barely even touching it, because most of what's going to happen is just going to fall due to gravity. So we have the force due to gravity over here, and the normal force barely anything at all. So compare all of these cases. Gravity stays the same. Notice that the normal force goes from full-blown gravity, where Fn equals Fg, to, well, we don't know about this one yet. We have to analyze it still. But all the way to normal force being 0. Now, here is something I want to ask you, and make a prediction before we do everything else. Make a prediction on what you think normal force is. Will the normal force on an incline be equal to that of gravity? Will it be greater to the value of gravity? Or will it be less compared to the value of gravity? What do you think? Make a prediction now. Alright, let's analyze this even more to see what we get from it. So we've drawn the free body diagram of these 3 objects. So let's answer some questions. Will the object on the incline move? Well, duh, yes, it will. We use a free body diagram to explain. We will actually have to come back to that one. Will this object accelerate down the incline at the acceleration due to gravity? So here's the question. We know this object's going to go down the incline, but will we know, or do we know if it's going to be that of gravity? We don't know about that one, so we will have to analyze it using our free body diagram. Now, how do we use this free body diagram? How do we deal with a case where we're dealing with an incline with an angle? Let's go down here for the key point. Since our motion is now on a diagonal axis, we will have to use a new set of axes where we're going to resolve our vectors into the components relative to a new set of axes. So what kind of axes should we use? Whenever you deal with an acceleration in a certain direction, a rule of thumb is you always want to choose one of your axes to be in the same direction as your acceleration. So imagine before we've dealt with x and y like this. But now what I'm going to do is I'm going to take this whole thing and I'm going to rotate it in a way so my x-axis is now on an angle like this. Okay, so that is my new set of axes going down the incline. I want one of my axes going down the incline because the object is accelerating down the incline. As a result, my y-axis will have to rotate as well. And it just so happens that it is perpendicular to the x-axis and in the same direction as Fn. That's actually very useful to us because we will be able to analyze the effects of Fn and how it may affect the force of friction when we deal with an incline. For the sake of simplicity, we're going to assume that this incline here is frictionless. So what I'm going to write that rule of thumb over here is that you always want to choose one of your axes in the same direction as acceleration. And as a result, your other axes will probably be perpendicular to that first axis you set up, which is going to be working towards your favor in this case. So now I have my new axes, and I am going to want to resolve my forces into their components. So notice that the normal force is already in my y-axis. I don't need to do anything there anymore. However, FG has components along the x-axis and the y-axis. So let's draw this one over here. Now keep in mind that no component will ever be longer than the original vector itself. So my force due to gravity is going to come all the way down here where it's going to meet this tip of the arrow over here, and this is going to be my FGY, my vertical or my y component of my gravity. Also, I have the x component of my gravity going along the same direction as my x-axis, and this is my x component of my force due to gravity. The next question is, well, if I want to write these out in terms of FG, I need an angle somewhere. Most of the cases, you're going to get an angle that's associated with the angle of the incline. So let's say you know this angle over here. Let's say you know theta as the angle of the incline. Let's look at some geometric analyses to help us determine where this angle goes inside this triangle with our forces. Keep in mind that this angle here is our 90-degree right triangle right over here. So let's take a look at our right triangles to help us analyze all of this. Take a look at this triangle over here. Now notice that this triangle is our right triangle, if I set this as my right triangle. And if this is my theta, let's say this is 30 degrees, then you know that this angle over here must be 90 degrees minus this 30 degrees over here. 90 minus 30, 60. Okay, so this is the complementary angle up over here. So let's get into this triangle involving our gravity. Notice that this angle between my 60 degrees and my y-axis, notice this guy here is 90 degrees. Which means if this is 60 degrees over here, then this guy, the complementary angle of that 90 degrees must be 30. 90 minus 60, 30. Which means that this angle inside this triangle, the angle between my FG and my y-axis, is the angle of my incline, based on geometric analyses. So anytime when you're confused about an angle, use the rules that you learn about geometry to help you figure out all those angles. So I have just left here the angle of our incline being theta, and this angle between FG and the y-axis is our angle theta, which gives us now the ability to write FGX and FGY in terms of FG based on this right triangle. This is our 90-degree angle over here. So if we take a look at FGX, notice this is opposite to our angle over there, which makes it FG opposite of that angle being sine of theta. I am not going to go over how I got this, but this is based on SOHCAHTOA trig rules. Go over this one and make sure you're very familiar with it. Next up, we have FGY. FGY, notice it is the adjacent side of our theta. I am going to call this FG cosine of theta. And these are the two components of my gravity. Notice that either of these is definitely going to be less than FG. This one is definitely going to be less than FG because why? Take a look at the components. Any component of any original force is always going to be less than your original one. And if you don't believe me, try substituting any angle that is less than 90 between 0 and 90 degrees, and you will find that your component of FG is going to be less than the original FG itself. Okay, so this is important to take note of, especially later on. So there is how we take an incline, break down the forces into their components. The key is to use a different set of axes. Now, going back to our question, use a free body diagram to explain that the object will accelerate. Well, if you take a look along the x-axis. Other than force of gravity in the x component, FGX, are there any forces acting along that line? You don't see anything. There's no other forces. Which means if we had to write an F net along the x direction, our F net, or the sum of our forces, is going to be FGX. And we know the FGX is greater than 0 as long as this object has mass, of course. Because that this FGX is greater than 0 and F net equals to ma, therefore, the acceleration cannot be 0 meters per second squared. Okay? So how does the object accelerate down the incline? Because of FGX, because of a component of gravity. The next question is, will this object accelerate down the incline at the acceleration due to gravity? Why or why not? Well, let's take a look at this kind of relationship over here, looking at the acceleration of my object going down the incline. So let's take a look here. We have FGX is equal to F net. Okay, that's equal to F net. And this is equal to, this is equal to our mass of the object times acceleration. Let's use that FGX is equal to FG sine theta. So I'm going to substitute FG sine theta over here. I'm going to get FG sine theta equals to MA. Also, I know that FG is equal to MG. Here, I'll write a note over here. FG equals to MG. Therefore, I can say instead of FG, this is MG. Now, notice that my mass cancels out. Mass cancels out. This gives me acceleration is equal to gravity times sine of theta. From a mathematical perspective, if theta is between 0 degrees and 90 degrees, then there's no way for gravity sine theta to be greater than gravity itself. Why? Because sine theta between 0 and 90 degrees is less than 1. And because it's less than 1, your total gravity is going to be less than the original value. Okay? That's from a mathematical perspective. From a conceptual perspective, think of it this way. You know that FG sine theta is only a component of gravity, which is going to be less than Fg. If a force is less than Fg, then therefore the acceleration gravity, of course, is going to be less than that of gravity. So the object will not accelerate down due to gravity because it's only one component of a gravitational force that is accelerating the object, not the full-blown gravity itself. So those are some kind of things to think about when we're dealing with inclines. What we're going to do in the next video is, now that we kind of have an idea of how inclines work and how to draw a free body diagram for inclines, the next video I'm going to go over these 3 examples, and in the last video I'm going to touch on a more complex example relating to different forces of tension and friction. Well, actually not friction, just tension. So hopefully you've got something out of this video, and please stay tuned to watch the next one for more examples. Good luck on your questions and problem solving, and I'll see you in the next one. Bye now.